We have with us Mr. Jason Jones, CEO and co founder of HMT, who will be talking regarding merging metal AM with CNC machining.
Good afternoon, everyone. Great to be joining you from Texas in the USA. I'm mindful of the COVID situation, which we have been through a very difficult period ourselves a number of months back. And I wish comfort to each of you who are struggling right now, or perhaps loved ones are struggling. Please hang in there. As we shift our attention today to additive manufacturing, my name is Dr. Jason Joe, and I'm joining you from the company Hybrid Manufacturing Technologies. I've prepared a little overview of where additive has developed over the last couple of decades and some of the work that we are doing specifically to help make additive easier to adopt, especially metal additive 3D printing. So let's jump in and see if we can't discuss this in a little more detail. First, let's talk about where we're at. If we talk about where 3D printing is, I would draw a map and I would say we are here. Well, where is here exactly? If I zoom out, I would say, look, we're somewhere in between heavy prototyping adoption and beginning to make production parts. I would say early adopters have all been making prototypes, certainly in less dense materials. And additive is a very powerful tool for making prototypes. As we look forward now to making production parts, in 2009, I helped found the ASTM standards body, the F42 Committee for Additive Manufacturing, and we named ourselves Additive Manufacturing. At the time we did that, this title was a little bit aspirational in that there were some manufactured parts, end-use parts, but most of the parts were still in prototyping phase. So we're very pleased this is now starting. It started in earnest by early adopters and it is now growing in adoption. It's still relatively early in making production parts, particularly with metal and ceramics and some other mixed materials. As we look forward, we go from prototyping to production parts, and looking to the future, we see a very bright future for smart products where you've got embedded intelligence made into those. We're in the middle one. As we move along this progression, we don't drop applications in prototyping. It continues to form a very solid and strong foundation. But in terms of application frequency, I would draw it as a pyramid where many people are using this technology for prototyping. A smaller amount, but growing number of individuals are using it for production parts. And right now, there are just a few applications where we see embedded intelligence with sensors and other things, and lots of growth opportunity in that upper part of the pyramid. So, materials matter in additive. How fast we develop materials often enables that adoption rate, right? It speeds it up. And if we think about materials themselves, we draw this little, we lay out these materials on a circular wheel, metal, polymer, ceramics, and there are others as well, but that represents the majority of materials that we deal with in additive. And if we think about where they've been used, most of the prototyping that was early developed in the mid to late 80s and then into the 90s and early 2000s, much of it was centered around polymers and lower density materials. As we look toward production parts, of course, there are polymer parts that are certainly great production parts. But one big shift is the ability to print metal. And that's really increased dramatically in the last decade and will continue to increase those higher density parts. Normally, we don't do very much prototyping in metal, at least at our company, we don't. Most often, we're making parts that will really be used in functional applications. Additionally, we see progress in ceramics and even some electronics. And as we look to what materials are needed for smart products, all of those materials are needed, even all of them in the same part. So mixing them together. And again, looking at these different material combinations and their many applications, it's a very exciting time for additive. So if we look at additive or 3D printing, there are 7 families, according to the standards bodies. That's 7 different sets of physics. And I've shown them here. You'll see this is a multicolored chart. You can download a copy of this for yourselves from hybridmanutech.com/resources. And each of the 7 families has unique capabilities. They're all good at something. That's why they all exist. And something they share in common, because additive began really with prototyping applications, most additive systems are made with a self-contained architecture. What that means is if you want to use more than one of the 7 different types of additive, then you normally end up requiring different machines for each type of additive. That works really well in a design and prototyping environment. As the mentality shifts from prototyping to production, this creates a couple of limitations. And first off, it's important to realize the first couple of decades for 3D printing was mostly in isolation from mainstream manufacturing. So they didn't intermingle that much. Furthermore, the different types of additive, I show them as if they're in prison, each within their own cell. They don't really talk to one another, right? They don't interact very much. You can't normally use multiple types of 3D printing on a single part. And so that segregated use limits additive in some ways. With the transition from lower density to higher density materials, especially metals, the typical post-process workflow got more complicated. 3D printing, often a metal printed part, then requires some amount of heat treat. After heat treat, of course, it has to cool down. Then normally it's removed from whatever the build platform is. The outside surface needs to be finished, often by milling, drilling, grinding, polishing, etc. And then additive creates some unique needs from an inspection standpoint. We do inspection more intensively after a part is made, and it's the techniques that are required. Often we're trying to look at the inside as well as the outside of a part at the same time. So as a result, when it comes to metal printed parts, often up to half of the cost of a 3D printed metal part comes from these downstream post-processing or post-print activities. So, and normally it's, somebody has to move these parts from one stage to the next. This self-contained nature reminds me a little bit of how computing was before the internet. Each computer had tremendous power, but it didn't realize its full potential until we brought them all together. Of course, we all know what it's like to have a smartphone, and that brings together many devices that used to be used independently and with a synergistic effect, right? It's a much better solution because you can say, use the GPS coordinates on a GPS tracker to also show up where your photos were taken. All of this combination is what brings a tremendous amount of added value. So looking at the different types, 7 different types of additive and the post-processing steps typically required, many of these 7 technologies can make parts in metal. And what you have to do to them afterwards varies depending on the set of physics that's been used. But look from this image and just realize that there are these downstream steps. When we talk about 3D printing, mostly we're talking about forming and fusing. I'd like to broaden your view to understand when we go to additive manufacturing, that full spectrum of manufacturing requires more than just forming and fusing. But to be on the same page, when I talk about forming, I'm talking about creating a shape. And if you look carefully, you can see we've used puzzle pieces to represent this forming, geometrical shaping, if you will. Normally, forming happens by layers, right? Cross-sectional layers through a part. The fusing step is a consolidating step. So I use fusing in a broad sense. Often it uses heat, but not always. Things can be fused chemically or using solid state methods, and different additive techniques rely on different things. But this forming and fusing, those are the primary activities of additive, and they're not always done in the same step. You might have something like a fused filament fabrication or FFF process that prints a form with metal powder bound in plastic, and then as a second step, have to go and sinter that, right, in an oven to be able to get to a metal part that's mostly damaged. So once metal parts are printed, typically the surface is rough like sandpaper. And so an additional step is needed for finishing. And the accuracy that drives, your application drives the accuracy needed. Very often, 3D printed metal parts end up inside of a CNC machine for that final tolerance and finish. And then the finalization steps really are the quality assurance and other things that you need to know your part is good and ready to be used in its end application. So those 4 F's, the forming, fusing, finishing, and finalizing, really need to all be considered together to get to true manufacturing or additive manufacturing, as the name of the technology implies. So generic thinking about automation says, okay, there's these 4 types of steps you have to go through. Why not simply put a robot at each of the transitions, and therefore you get to move things downstream? And that certainly works for some contexts, and indeed you can find solutions now which are robotically based that move parts along, and sometimes even the robots are used to actually direct the path, the deposition path as well. In other contexts, you think, wait a minute, if I'm going to have to finish these parts and they end up inside of a CNC machine or a grinder, instead of using lots of robots between each thing, could we not also consider that a CNC machine might also be a common denominator or a base, right? A common base to house all of these different steps. And that's what we've focused on as a company, is integrating these different steps into a common platform, an appropriate platform, often a CNC machine, to be able to make them all go together. So let me give you a brief overview of what it looks like to go through these 4 different steps altogether. So diving in machining, or maybe even a die casting type process. So we end up needing to do some additional steps. And you can see in this image, this is courtesy of Siaki. It's a directed to complementary technologies needed to make it really work robustly, quickly, and efficiently. Our trade name is AMBIT, Advanced Manufacturer by Integrated Technologies. And if you look above this CNC machine, we've got silhouettes illustrating subtractive techniques like turning and milling and drilling. The next row down, we've got these 3D printing techniques represented. And then that bottom rung with the triangle and the microscope represent inspection. So pictographically, trying to communicate that, we have integrated that into our logo. You'll notice there's 3 tools in that logo that represent inspection, subtraction, and additive all together. Expanding those 3 out, what you see on screen now are different tool heads, each dedicated to a different function. So some are for adding metal, some are for adding, polymer reinforced composites. Others are for doing things like laser drilling, and even some are for inspection. If we can modularize these and move them around, then you can interchange between the different processes that you need. And as a company, we've worked hard to modularize these so that they fit inside of CNC machines and robots and gantries, whatever the most appropriate platform is for the size and accuracy of the parts that you need. So if we look in some detail, this is a tooling insert with high performance edges. To be able to really have a good idea of what's there, I'd like to show you this video. So watch carefully. This is looking inside of a CNC machine. And what you see on the left is a tool head which can be loaded into the CNC spindle, and it will then be able to deposit onto the part. So as you just saw in that video, the objective here is to take this tooling insert and to be able to get about a 2 to 3 times improvement in its service life. That is achieved only by 3D printing along the edges of this part. The entire part does not need to be printed, but just adding those edges where the wear happens, you can often triple the lifetime of this part. Now, the cost to do that, if you see right here behind my hand, about $13 US to add those hard edges. So if this particular tooling insert is worth, let's suppose that it costs you, 50 to 150 US dollars to make, its sale price could be double that. Why would you not spend the additional $13 to be able to make something that lasts twice as long or 3 times as long? This approach enables a much higher value product, a longer performing product. And it's done in a very short cycle time. It adds less than 10 minutes to the cycle time of this part. It can be done in the same setup as what you're already using to do the essential processing anyway. So there's no additional, refixturing and moving it along. And it enables a no faults forward approach. You get to move downstream with confidence, right? Knowing that your part is good for your final customer, which is a great place to be. So this hybrid approach where we can move between the forming, fusing, finishing, and finalizing all in the same setup, it is the most cost-effective approach from a time and money perspective to get this particular part made. So let's look at some other applications and where this kind of fits in. We often lay out our applications often with industry verticals across the top, right? So tool and die, and oil and gas, power generation. Along the left-hand side, you'll also notice, though, we have kind of build parts from scratch at the top. That's how most people imagine additive. You start with nothing, you build the whole thing up. Yes, that has a strong value proposition for some applications. There are also times where you only need to print a proportion of the part. So you see adding features is next, or maybe just coatings, right? Or which is a little bit more how that tooling insert that we showed works. You're really only adding coatings at the edges, or repairing where you're building something back up. So we use this scale to kind of explain how designs, how ready they are for immediate additive adoption. At the very bottom, you'll notice that to repair something, usually you can use an existing design. Immediately, it can use additive for repair, coatings, sometimes even for adding features. As you get into adding features and especially printing parts from scratch, to get the full value proposition, normally part redesign is desirable and necessary to really get the full value out of these parts. So equally, that same vertical axis, we talk about the percentage of the part being printed. When you print from scratch, clearly you're printing 100% of those parts, and then it comes down to even less than 25. Sometimes with coatings, it's even less than 1% of the weight or volume of those parts. So the adoption effort required from the bottom left-hand corner to the upper right increases as you get to more and more regulated businesses, as well as increasing the proportion of the part that you're building. So here's kind of a quick look at some of the different applications that fit into these different spaces. And I'd like to show you in detail. This is an example from one of our customers, the AFRC, and it's a gear where 3 of the teeth were damaged and removed. And we'll record that in a second, showing the rebuilding of the individual teeth on that gear. Likewise, being able to add coatings. This is a sealing face for an oil and gas part. Here we show adding features. So you can see growing up, spigots and often flanges and other things that work well too. So again, another opportunity to be able to add value by building these things up. And finally, you see here a part that has been made with different materials. This is a mixture of stainless steel and bronze so that you can leverage the properties of 2 different materials at once and really get to something that you can't get to with a single material part. So a very exciting application space is created when we move to this additive approach, and we can use multiple materials fit inside of the forming, fusing, finishing, and finalizing sequence. So as we move toward wrapping up, I have a very exciting announcement for India. We have actually just partnered with Excel 3D to support and sell our equipment in India. They are based in Mumbai, and we're very pleased to be partnering with Samit and Ukarsha and the rest of their team at Excel 3D. And we recommend that you reach out to them as you have questions and opportunities and want to learn more about this exciting technology. So I thank you very much for the opportunity to speak with you today. I hope this overview has provided you context for how additive has shifted from lower density materials like polymers into metals and ceramics, and now starting to intermingle some of those different materials. And the future is very bright for additive. Continue to learn about it and how it fits into the more traditional types of manufacturing techniques. Thank you very much.
Thank you for the amazing session. Hope you have learned a lot from this session.